So welcome to Intro to R Package Part 2, which is part of our 2016 How-To Talks by Postdoc series. Dr. Anna Nagle is going to be leading today's workshop to show you more that you can do with R. And for those of you who were not here last week, she received her Ph.D. in biomedical engineering from the University of Cincinnati and is currently a postdoc at VCU in the Mechanical and Nuclear Engineering Department. Please welcome Dr. Nagle.
Thank you. So today I'm not using a microphone. Can everyone hear me?
Yes.
Awesome. So I want you all to start at the Wikispace page. This is the same page we used last time, or rather the same site we used last time, but within there are several pages. And I'm going to quick show you what they are. Let me switch overs there. So if you go to this URL, it's vcu-r.wikispaces.com. And once you reach here, on this right-hand side is all the pages that go with this. And what we worked on last week was Welcome to R. So if some of you don't maybe feel like watching the whole recording, you could just click on this link and it will take you through that whole lesson again if you need to review anything. And first I want to show you this page, which is new. So this is a list of helpful links. So Kara and I looked at your responses from last week, and there were some things you guys were interested in that I do not know how to do. And instead of trying to wing it and tell you the wrong thing, we thought it would make sense to direct you to the places that actually will do a better job of showing you how to do certain things. So the first couple are online through VCU. You can go to Pluralsight or Lynda. VCU Libraries has a number of books on R. Scrolling down, the next few links are things that I have favorited on my browsers because I go to these sites a lot. And within those, I'll search for the thing I'm looking for it to do. And finally, if you can't actually find help trying to do what you're doing, there are forums where you can ask other users of R how to do it, and folks will hopefully respond to you. And also, what I usually do is search through responses that have already occurred that might be addressing my questions. And pages of notes. Someone had asked about heat maps, which are cool, and I have no idea how to do them. But there's a really nice resource through R bloggers on how to create those. And likewise for 3D plots, I do all of my 3D plots in MATLAB. I don't actually do it in R. But they also have a really nice site on how to do 3D plots that will take you step by step. So this will stay up, so even if you don't hear what you wanted to learn through my talk, I highly recommend you check out these sites. But now to go to what we're doing today, we will be going through this page called Using R with Packages. And last week, I went through a series of different examples. This is actually going to all be using one example from my research that will take you through the different processes I do when I'm trying to analyze that data. So the first thing we need to work on, which might be really fast and might be really slow depending on computers, is start downloading packages. And we'll be using 3 packages today: FBasic, Power, and XLSX. I tried to practice on 2 different computers to make sure they would all work, and this last one didn't work on one of them, so I have a workaround if you have an issue with that one. But first, let's all go to R. Hopefully you have it up. And to see what packages you already have, you can click on this top menu bar, Packages, Load Package. And if you look at this list, I don't have any of those 3 packages that I'm going to need today, so I need to download them now. If you had it, you could just double click on it and it would be loaded into your library. So I'm going to again click on Packages from top menu bar and then Install Packages. And now it's going to ask me to use a mirror. Just like when we downloaded R, you might have been asked to use a mirror. This is the same type of thing. And I'm going to scroll down and use USA, Tennessee, because it's probably the closest. Really, you should be able to pick any of them. And then from here, the first, I should probably make this so that we can see both. But the first package I want is F Basics, so I'm going to scroll down on this till I find F Basics. And I'm going to double click it. You may or may not get this question, would you like to use your personal library? On this computer, I have to say yes. On other computers, you might have to say no, so this is why it might take a minute. And I am actually going to make the font size on the console bigger so that folks in the back can see it a little better. So I'm going to edit GUI preferences and changing the font size here. And now I need it all to fit. There. Is that a little easier for you to see in the back? So it's a good size? Okay. Did anyone have trouble downloading F Basics? Did you get something that looks like this? If you got an error, raise your hand and Karen or Dana will look on. Because there are a lot of possible errors at this point. And if you were successful, go ahead and install the 2 other packages we'll be using today. So the next one is Power PWR.
So I need to be a user.
I don't think so, because when you...
But when you open it next thing, it's not there. Then it installs.
It depends how your computer is set. With mine, once I've installed it, it stays. But like with the loaner laptops, when you log off, it wipes everything. So if it's your personal laptop, you'll probably have it to keep. So I'm going to go ahead and install that final package, which was XLSX.
Yeah. So yeah, so the next one shows it's done. Install. Try that.
And then, I know some of you are still downloading, but for everyone else, type in library, parentheses, XLSX if you have downloaded that package yet, and see if you get an error, because I think if there's going to be an error anywhere, that's the likely place. This library requires Java, and if your computer isn't running the right type, it might not work. That's funny. I just downloaded that, I thought. Okay, and it's not even working for me. So let me try this again. Let me try now. That didn't work. I'm gonna try closing and starting with the other R that was 64-bit. And before you all got here, I tried this on 32-bit to make sure it worked, and it worked there. So if it doesn't work for the 64 version of R, and you also have the 32, try that, because at least on this system, it's only working on the 32. And if none of that works, I will show the workaround. Yes?
The packages, do
Yeah.
they tend to be specific to the version
So,
32, 64?
They're supposed to work with either. Sometimes they don't. The funny thing is, at home, on my home computer, this package works with 64-bit R, but on this computer it isn't. So I'm not sure why. Must be some intricacy with this is a different computer with its own permissions, and the way I downloaded it was a bit different too.
I just have an error.
Okay,
So-
let me quick see if it's an error I know how to deal with.
So I went
Okay.
and downloaded the one that
Mhm.
said that, and it still.
Okay, so this is the Java issue. And that one, you kind of have to like reinstall everything, including Java, which takes a while. So I will show you.
You can use this one.
Yeah, or we can switch
You have another one.
computers for now.
You'll have to load the packages on here.
This one, I was saying, you go ahead and use that one and I'll download it.
No.
Okay.
You want to download this first.
You'll have to download the package.
Does anyone else have an issue? Because we do have one more loaner laptop.
Save it for the next era.
Okay. I think this is the thing with the most errors, so I just kind of want to get it out of the way to start. From here on out, we'll be smooth sailing. Well, smoother. Okay, let me readjust this. I'm gonna make this a bigger font size again. And now I'm gonna start talking about the data. So on the wiki page, click on download on the practice data, assuming that you got the XLS library to load. If not, I did put the data in text files in case that was going to be an issue for folks. And now I'm going to tell you about my research. So I look at people with overactive bladder, and I want to know what's different about how they feel bladder sensation versus the general population. So what I have in here is, oh, I should leave that. Anyhow, what I have in here is on the first sheet, I have data from normal participants in a hydration study. We had them drink a bunch of Gatorade, and they told us when they felt a really strong desire to void, and then we let them void and we measured the volume. And we want to see if we do this twice in a row, is there a difference? Because there is research showing that on the suck and fill, you feel sensations differently because you've trained yourself to listen to your bladder more. So we're looking at that effective training. And so what I have here is fill 1, and these are just the subject numbers of the participants. Over here I have strong desire, volume at that strong desire to void, and these are in milliliters. And then I have fill 2, the same people, and then I have the volumes at that second void. And then on the next tab, I have the same data for people with overactive bladder. These are different participants. And I want to know, is training in a person with normal bladder sensation the same as the training in someone with overactive bladder? Is that something that's going wrong, or is it other issues? So one thing that I have in this data set that will not make R happy, but it will be okay, is my titles. If you look up here, I have SD space VOL. R does not like spaces in titles, because then when I call for that list, it's going to misinterpret that space. But you'll see when we load it in, it will actually fix it for us. So let me go back here so we can follow along. So I do have a link to the journal article on this if you're curious about how all this research turned out. So first we're going to load in the data, and we're going to do this the same way, more or less the same way we did last week, where first we have to set the directory to where our data actually is. So I'm first going to find out where the current directory is. Hopefully you can see everything now. Get working directory is WD. So right now it's looking in documents, and I know I downloaded it to the downloads folder. So now I'm going to do set WD, and I'm just going to copy and paste the part of this that's correct, and then we'll put in downloads, so that it will be looking in the directory where I have my data.
Is it different for Macs?
The difference for Macs is that you don't have to worry about the direction of the slashes. On your Windows computers, if you were to go to the actual location and look at the full list, it would have the slashes going the wrong way, and you would have to delete them and make them the backslash instead of the forward slash. Macs should already be that direction. So in that way, R is a little more compatible with Macs than Windows, but in other ways it's a little easier on Windows, so I think it's a wash, which you use. And now I'm going to load in the data. I would encourage you to type it out, but if you have issues, you can always just copy and paste directly from the wiki page and see if that works. And if it still doesn't work after you copy and paste, raise your hand so we can come help you. So in this Excel doc, let me open the one that looks like the one you have. I only have 2 sheets, and I'm going to load them both into different data tables. So I'm going to call the first data table norm for the people with normal bladder sensation. And I'm going to define that as read.xlsx, and then in quotations the name of the file, which is practicedata.xlsx, and quotation, comma, sheet name. And the sheet name is also no quotations, and that's normal with a capital N. And now let me look at that data. And if you look at the headings, you'll notice that where I had a space, it has now put a dot. So now I won't have any issues if I'm trying to look at a specific column. I'm going to write it the way R sees it, SD.vol. The other thing it didn't like is I had 2 separate columns that had the same name. This had been SD.vol inside this last column, and that's going to be confusing if I tell it to look at a column called SD.vol, and there's 2 of them, it doesn't know which one. So it renamed the second one SD.vol.1. So it actually fixed all my mistakes, which is awesome. But it does mean when you're using R, you do have to open it up and make sure it hasn't changed any headings on you, and not assume it used the headings you thought you told it to use. It's going to adjust them to make it happy.
What if you have a big file so that you can see
So it is a little annoying when you have a really big file and then you're like, I want to see that, and it takes everything. So in that case, I would encourage you to change your headings beforehand. Because there's really two things R doesn't like: spaces and repeated column names. So you could just take care of it before you ever import it into R, and then you'll know that R will keep the names you told it. And kind of skip this step. Is everyone able to get to the data? Okay, there's someone back here. Anyone else? Okay, now let me import the data from the OAB group. So I have the normals. Now I'm going to do the same thing to import the data. And remember, you can click the up button to see the commands you just used. And since I don't feel like retyping everything, I'm just going to do that, and I'm going to replace the word normal with OAB. And I'm going to scroll over here and type in OAB again. So now this will be .oab. And then it did the same thing with this data. It renamed my headings to work within its own logic. And then I put stuff for the text documents, but I think no one's using those. So we can move onward. Any questions on importing the data? I think so. All right. So the next thing we're going to look at is the data normally distributed? And when I say normally distributed, I mean if we took all the data and you made a histogram, look at the distribution, would it look like a normal Gaussian bell shape with a big peak on the middle and pretty symmetric and kind of tails off on the sides? So like if we took the heights of everyone in this room, we could probably make a histogram, and maybe there'd be peak around 5'8" or whatever is average, and then people on either side of that, but fewer and fewer people on either side of the average. And generally, at least with looking at biological things, if you're looking in a population, you have enough samples, and it's just randomly picked out people or individuals from that population, it is very likely going to have a normal distribution. And so a lot of the statistical tools we use assume that we'll have a normal distribution. So we're going to use tools from the Finance Basics library. So we're going to put in library F Basics that you downloaded earlier. And hopefully you get something that looks like this. Please raise your hand if you did not. And this library has a number of different normality test methods. And if I were a statistician, I would tell you all about the nitty-gritty, any workings in those methods. But I'm an engineer, and that's not really my field. What I want to know is which test do I use for what type of data. So when I took statistics like 10 years ago, I was told to use the Kolmogorov-Smirnov test, KS for short. But now that's considered outdated. It's just the people teaching me were older and I guess not keeping up. So there will be times you'll want to use that test because you want to see if how your data compares to really old data, but that's like what they used in the 50s. It's not really the best method now. We have newer methods that are more powerful that you should be using instead. What is often most recommended is the Pearson test. The issue with that is, at least in R, it requires 20 data points. And if you notice, I only have 12 data points, so that's not going to work. Another very common one is the Jack-Barra test. And that's one where I could use it. It wouldn't fail like the VA test. But it's more powerful the higher number of values, and I don't have that many values. So what I'm going to use is the Shapiro test, which is actually the default setting for normality tests, so that's kind of convenient. The issue with this is it works best if every value is unique. But if you look at my values, they're all unique. You don't see any value repeating itself. So that's what's going to work best for this data. So we're going to use the Shapiro test. And if you don't want to memorize what the little 2-letter abbreviations for everything are, I should have showed you this yesterday. If you know the name of the function you're using, in this case normal test, you can write question mark the name of the function. And it will link to the R server if you have internet, and will bring up the documentation on it. And that works with pretty much any function from R. So you can always look up how to use it. They usually have some examples at the bottom. They'll tell you about the test. So I'm not big into memorizing everything. I often do question mark name of the test, so I remember how exactly to use it. So I'm gonna write normal test, be sure to capitalize the T in test, and I'm gonna do the OAB people first. Actually, I don't know why I'm doing the OAB people first. I thought I was going to do the normals first. I'm gonna do normals first, sorry. I'm changing my mind from what I wrote in Wiki, just to keep things in the same order we've been doing. So dat norm, and then remember the $ tells which columns to look at. And I'm gonna look at the first list of volumes, SV vol, and I'm gonna tell it method equal SW for the Shapiro Wilk. And now it's going to give me data. And here what I'm looking for is what is the p-value, like usual. In this case, the null hypothesis is that our data is normal. Like, we take normal people, they're just random people who participate in the study. If you measure their bladder volumes, it might make sense for that to follow a normal curve. And since the p-value is quite high, we cannot reject that null hypothesis. So we're going to treat this data as following a normal distribution. And so we can use our standard statistical tools like t-tests, and we should be able to trust them because they're assuming the data follows a normal distribution, and it looks like that's true. Does that concept make sense to everyone? So now I want to do the same thing for all of the other columns of data. So I'm going to use my up key to get this back, and then I want to look at the second column from the normals. And again, the p-value is quite high, so we're going to say, I think this data follows a normal distribution. Now I'm going to look at my OAB people. And here, I don't really know for sure if it would be a normal distribution or not, because these were not random people. These are people who specifically recruited because they have abnormal bladder sensation. So it might not be reasonable to expect it to follow a normal curve, but that's still our default assumption, so that's our null hypothesis. And for that first volume, it's not as high a p-value as the others, but still quite high, so we're going to say normal enough. We can still consider that following a normal curve. And now let's look at that last column from the OAB people for fill 2. And now we see that the p-value is really quite low. If I use my standard cutoff at 0.05, this is way lower than that. So that means maybe I shouldn't use the standard statistical test because they're going to assume that this follows a normal distribution, and it looks like it does not. And if I'm wondering, is R lying to me? I can look at a histogram of the data and see if I agree with it. So I'm going to write hist, and first I'm going to look at that first column of the OAB group. So that's stat OAB $SV.vol. And I need to expand this to see the plot. Oh. I know. I need to capitalize my D. So this is the one where it said, well, maybe it's not quite as normal as those others, but still close to normal. And if you look at this plot, you can see it's a little skewed to the left, but it still has a peak and then trails off on either side. So probably close enough to normal for our test to be valid. And now I want to look at a histogram of the one that failed that normality test, that last column data. And now it looks like we have a bunch of people kind of crammed into this area and then like one complete outlier just skewing everything. And probably if we didn't have this individual, it might be close enough to normal for our normal test to work. But it's not really fair to just exclude them because we don't like the data. So we're going to keep them, and that gives us an excuse to look at other methods of comparing means besides t-tests that work for non-normal data. The interesting thing about overactive bladder is if you look at these sizes, most people are in this like maxed out at 400 milliliter bladder capacity. If we look at, for example, our normals, they're going to be much higher. So here it looks like the average bladder capacity is more like 600 in the normal population. So that part does make sense that people with overactive bladder might have to ward earlier. That goes with the symptoms of that disease. So let me bring back my Lilke so we can follow along more easily. So here's the histograms. We've looked at the normality tests. And I mentioned that we're going to end up looking at some tests other than t-tests to compare means. What I'm going to use here is the Wilcoxon Test. It's basically like a paired t-test, but it doesn't assume everything is a normal distribution, so it's considered non-parametric. Non-parametric means that it's just making no assumptions. And so instead of actually using the data initially just as those data points, it's actually going to assign each data point a rank and compare those ranks instead of the data directly to deal with this non-normal distribution. And I have a link here, and I'm going to show you that link again later on because it has a lot of great information on dealing with non-parametric data, including a table of the parametric test and its non-parametric equivalent. So today I'm going to show you t-tests, but for example, if you had more data and you wanted to do ANOVA, it will tell you about how to do the non-parametric version of that, which is also called a Wilcoxon test, but then it's Wilcoxon Man-Whitley-U test rather than Wilcoxon Sign Rank test. Clearly developed by the same individuals. So we did a little bit on t-tests last time, and we're going to continue that lesson. Last time we compared a population to an idealized value. Here we're going to compare two sets of columns of numbers to each other. So I want to know, is the bladder volume of fill 1 statistically different than fill 2? And I'm going to start with the normals because they follow normal distribution, so we can do what we're a little more used to, which is the t-test. If I can have both of these open at once, would be good. There. All right. And again, I would encourage you to type everything in so you get used to typing it, but if it doesn't work, just copy and paste from Lilke. So we're going to do the same function that we used last week, which is p.test, but the arguments are going to be a little different. So x is equal to dat norm $sd.vol, so the first column. And now instead of y being equal to a single number, we're going to do y equal dat norm $sd.vol.1. Now we're going to continue this. So alternative equals two-side, and that means that we don't know automatically which would be higher. You might have other examples where you know it should be greater or less than in the second round, but in this case, we don't know for sure if you would have higher bladder capacity before or after training. So that's two-sided in quotations. And then these are all data from the same individuals. So the data is paired. That means that it matters what column number you're on. Like the person from row 1 is still the person from row 1 in each column. So that's why we're going to write paired true. Paired equal true in all caps. And then our last argument is var dot equal. And this is asking, do you think the variances in these two lists of numbers are the same? Because that makes the math a little easier. But in this case, I don't know that that's the same assumption, so I'm going to write false there. Because for all I know, the variances are different. And now let's see what it gave us. So let me break down the output. So t equaled 2.1, that's a t-statistic. If it's positive, it means the second column was higher. If this were a negative number, it would mean the second column was lower. Degrees of freedom is the number of data points I gave it, -1. And then the p-value is what I'm really looking for, and that's telling me, is this statistically significantly different at whatever confidence interval I want, which is probably 95%, which would relate to a p-value of 0.05. And this is just on the border of being significant, so maybe I'd be like, well, maybe I'll change my p-value cutoff to be higher, but I would probably need like a good reason to do so, and I don't really have one. So it could be that if I brought in more participants and had more data, that difference between fill 1 and fill 2 might be significant, but right now I would still have to say I can't reject that null hypothesis. We can't say these two fills are significantly different, even though it looks like there's a trend that the second fill is higher. And then if you look at the 95% confidence interval, it goes through 0, which is to say they're not exactly different, but just barely, which is why I think if we added more people, it might be different in larger population, but not quite in this group. Any questions on the t-test? Okay, so now I'm going to do the Wilcoxon test. Because for the OAB group, I don't want to use the t-test. It's going to make a false assumption that everything is normally distributed, and so I won't be able to trust what it says. And the arguments for the Wilcoxon test are very similar. So, be nice to see both at once, though. Alright, so test OAB equal Wilcox.test. And again, x is equal to the first column of that OAB group. Now y is equal to the second column of the OAB group. Again, the alternative is two-sided because I don't know if the first one should be lower or higher. And again, I'm going to say paired equal to true because the columns are related. They're in the same individuals. Oops, I did not mean to return there. Hopefully this will still work. Okay, oh, I wrote to you. Yes.
Yes, D. You put
Oh, I made a typo. Thank you. And I must have made another typo.
You had capital B in your.
You're right, it's capital B. In both of them. Okay, I think that time it worked. Okay, and now looking at our results from the Wilcoxon sign value, this V value, I think is kind of analogous to that t-statistic, and that's positive, so maybe that second column's a little higher. But if you look at the p-value, which is really what I'm looking for, it's 0.33, that's not even near
that significance level of 0.05. So I would definitely reject the idea that fill 2 and fill 1 are specifically different in this population. And probably even if I added a few more people, that would still not be statistically different. So I cannot reject null hypothesis, so we're going to say fill 1 and fill 2 in both groups are not statistically different. Any question on the Wilcoxon test? Again, with this, if you forget all the arguments, you can type in question mark Wilcox dot, if you spell it right, Wilcox.test, and it will give you all of the things you might put in. So, for example, if your data isn't paired, you would write false. So if I wanted to compare my OIB group to my normal group, where they're different people, then I would write false if I were doing a Wilcox test for that. Okay, so now I want to talk about expert data and hope it works. Because kind of like importing data, we had a lot of issues. Exporting data has a lot of the same issues because it really depends on your system. So the easiest thing, if all this doesn't work, is you can just highlight all this and copy and paste it into your Excel doc or your Word doc or whatever. So if everything fails with exporting, just copy and paste. But I do like it when it does it automatically, so we're going to try that and I hope it works for most of you. So we're going to use the command write.xlsx. And the thing we're going to write first is the results of the normal test. And we need the command unlist first because all that data is in list form and Excel doesn't like that for some reason. Or rather, the Excel package doesn't like that in list form. So you just have to trick it into thinking it's not a list. Now we need to tell it where to put that data. And I want it to go into that Excel doc right here. Clearly I already practiced because it's here. But I want it to make a new tab in this existing Excel doc. But for that to work, I actually need to close this because it can't write to a document that's open. And then in quotations, put the name of the file.
Preface data. Preface data.
Oh, yes, thank you. If I had continued, it would have just made a new Excel doc called practice when it didn't see anything named that. So it's sheet, name, and I'm going to give it a new sheet called test norm. I want it to include the column name, so I'm going to write column names equal true. And likewise, I would like it to print off the row names. So row.names equal true. If you have a situation where that's just going to look cluttery, just write false in capital letters there. And I don't want it to completely overwrite the document. I want to keep the data I already have, so I'm going to write append equal to true. And then I don't know what show NA means. I just always say true. And I probably made a typo in there. So I'm going to do the shortcut and copy and paste from this so we don't run out of time. Oh, and it still didn't work. So it doesn't, maybe it's because I've already made that sheet. So now I'm going to do it for the OIB, which does not yet have a sheet in there. Okay, so it doesn't like making a sheet when that sheet already exists. That makes sense. So now if I go back to my Excel document, it should have both test norm and test OIB. Is everyone able to write to Excel? Awesome. So there's one more thing I want to show you, and now we have just enough time to do it. So let me close out of here. And now the power analysis, which is probably like the most important thing I use Excel for. So of course I saved it for last. So we're going to use the power library, which you can either write library of power like here, or the other way to load packages is from packages on that top menu, and just find it here, and double click it. And you should, if there's an error message, raise your hand. But I think the power library doesn't rely on Java the way the Excel library does, so it will probably work for everyone. So, yeah, if you notice with my normals, it looked like maybe if I add enough more people, I might have enough data to measure a significant difference between fill 1 and fill 2. So I'm going to try and measure that. So if we're planning a t-test, we're going to use, I'm just going to go ahead and show you the documentation. It's power.t.test. And this is going to say if we're planning a t-test in the future, and we want to know n, the number of individuals, we can put in a d, which is effect size, a significance level, and a power level that we desire, and it will pop out n, the number of people we need. On the other hand, if we already know how many people we can afford, we can put in like 30 for n, and then we tell it what effect size and significant level and pop out the power. So of those 4 things, you can leave out one of them, and it will tell you the missing one. But what I usually want to know is, if I had infinite money, what would my ideal subject population be? How many people do I need? And the tough thing is, at least I find, measuring the effect size, because that you need some prior data from, and sometimes you don't have much prior data. But at least in this case, we've already done the pilot study, so that data we already have in is going to help us figure out our effect size. So the effect size is the difference in means divided by the standard deviation. So I want to look at the effect size between fill 1 and fill 2 between the normal population. So I'm going to measure those 2 means. So I'm going to call the first one mean 1 and define that as the mean of that norm $sd.vol. And then the same thing for me too. And then the really tricky thing is I don't just need the difference in those 2 means, I also need to divide that difference by the standard deviation. And there are going to be a lot of cases where you don't know the standard deviation for one of those. So if you have standard deviation for one set, just use that. That's actually what people use most often. In my case, I can calculate standard deviation for both these columns, so I'm going to go ahead and do that and take the mean of them and use that as my standard deviation in the denominator for the effect size. So I'm going to call this SD1. Actually, I'm just going to save myself from typing and replace the word mean with SD. And the same with SD2. And for some reason, it doesn't like it if I just automatically ask for mean of SD1, SD2. It likes me to put them in a column vector together. So that is on this line down here. So I'm going to call the standard deviation Mr. SDS. Going to define it as a column vector of SD1 and SD2. And just check on that. There's SD2. Okay, so I have my 2 standard deviations, and then the SD I'm going to take as the mean of those 2. SDS. And now my effect size I'm calling del is really the absolute value of mean 1 minus mean 2 over SD. And actually I think, if I remember right, mean 2 is larger 1, so I'm going to just reverse those. Mean 2 minus mean 1 over SD. Oh, I should have done it the other way. Sorry, I remembered it being the other way. So this is the effect size. It's saying that if I can measure this amount of change, that is clinically significant. And that really will depend on what kind of prior data you have access to, how well you can measure what effect size is significant for your project. Like I said, there will be times where you just have to make a guess at what that target mean will be and just use the standard deviation from your first set of values. So now we'll go ahead and do the power test. So I'm going to call this n because we're asking for the number of people. Power.t.test equals n equal null, comma d equal del. And I'm going to use my usual significance level of 0.05. Obviously, in different fields, a different number might be used. I'm going to use power equal to 0.8. Again, that's kind of standard in my field, is 80% power, but it might be different for you. Again, now I have to think about what kind of t-test am I going to do, and it's going to be paired. So it's going to be a paired type 2 test. And it'll be nice to have the rest of my notes. Sorry. And again, we're going to do two-sided because we don't know in advance if one will be higher than the other. Two-sided and quotation. And now if I look at my n, it will pop back those 4 things, and it's filled in n that I need 51 subjects to conduct the study and tell if there really is a significant difference between fill 1 and fill 2 in the normal population. So I already had 14, so I have to recruit a bunch more people and somehow pay for that. But we would potentially be able to see the significant difference in training if we had 51 people. And this is in each group, but since it's the same group, that's just 51 people. If I, instead of typing in type paired, I had said unpaired, so like if I'm looking at differences between the OIB group and the normal group, then this would be per group, and it would be like 51 in each group. Any questions on that? Okay, we're running out of time, so I'm going to quick say what you do with the OAB group where it's not normal. So there's no power test for the Wilcoxon. It's only a power analysis for the t-test. And likewise for all the other non-parametric things, the best you can do is use the parametric version and then at the end adjust it, because the non-parametric version, even though it'll be more accurate, it'll be less powerful. So I'm going to show that on the Lilke page, and I was going to have it be an exercise, but we don't really have time for that, so I'll just add what to do afterwards. But basically, for any given non-parametric test, which is here, you have to figure out what the parametric version of it is, and then the ARE is the relative efficiency of that test. So this is saying that the Wilcoxon test has like 95.5% of the efficiency of the paired t-test. So when you get out a number for the paired t-test, you need to multiply it by 1 over 0.955, which is this, 1.04. And that's really the number you should plan on using for that set of subjects. So to quick recap, pretend it's normal data, do the power analysis as if it's going to be normal, and then at the end, multiply by 0.047, so it's going to raise that a little bit to compensate for it not being as powerful of a test, and that should be your target number. And it does depend on the test. I just put the 3 tests that I use here. And you'll notice that these numbers, they're not that far off from 1. Because even though these non-parametric tests aren't as powerful, they're pretty close. So the number you get is going to be pretty, you're not going to have to adjust it a lot. So that is a little reassuring, I feel. And like I said, I will fill in here, so if you come back here in an hour, I'll have the instructions on how to do that. But if you want to try it on your own first and see if you get the same answer as me, that would be cool. Or maybe I'll even put on another page so you can look at this and try it yourself, and then go to the next page and see if you get the same answer. Would that be better? Maybe? I'll try and do that. So give me a little bit of time, but it won't be long. And then if you come back to this page, on this right-hand side where it says all pages, I'll have like answer to Wilcox power analysis, and it will have all the steps and my final results. All right.
Okay.
Any questions? Well, thank you all for coming. I hope this is useful to you.
Thanks, Anna.
Thank you.